Okay, hello everyone. My name is Hanara, and I am a Senior Specialist SA for EC2 Graviton. And for today, we're going to be covering the latest release of PyTorch. That's PyTorch 2.0. And we'll also be talking about its performance on Graviton 3 and how to get your PyTorch workload started on Graviton as well. Okay, so the latest release of PyTorch has some significant updates that optimize performance on Graviton. On the previous PyTorch version, there were some parts that were not optimized for Arch64. So for some models, Graviton was just not the first choice, some machine learning models. So let's take a look at a couple graphs on how PyTorch 2.0 has improved performance on Graviton. And first, let's look at PyTorch 1.13 compared to PyTorch 2.0. So there's a really big jump in increase of speed for ResNet 50. There's a little bit more of an increase for BERT models. And so here's a quick overview of the jump that you can expect if you're moving from 1.13 to 2.0. So PyTorch 2.0 on Graviton 3, as we just saw, is 3.5 times faster for ResNet 50 and 1.4 times faster for BERT. So that is PyTorch 1.13 compared to 2.0. And that makes Graviton now the fastest compute optimized instance on AWS for those models. And when you make the jump to PyTorch 2.0, as well as Graviton 3, you can expect up to 50% cost savings, depending on which model you're using and which Graviton instance you're using as well. So how are these optimizations and the performance increase on Graviton possible? It's a combination of PyTorch 2.0 improvement from its previous version, as well as some new features that was added to Graviton 3 compared to its predecessor, Graviton 2. And PyTorch now supports ARM compute libraries, and the ACL provides Neon and SVE support, SVE optimized general matrix multiplication kernels for FP32 and bfloat16. So a combination of this with Graviton 3's new feature for supporting bfloat16 gives us a really nice pairing to get this performance increase. So Graviton 3 now allows us to enable deployments for models using bfloat16, FP32, and automatic mixed precision models. Additionally, FP32 models leverage the bfloat16 kernels through 1DNN fast math mode. That allows it to be 2 times faster in performance compared to existing FP32 models that do not leverage that feature. And you can also use bfloat16 models with the bfloat16 kernels with FP32 models without model quantization as well, while also getting performance increase, which is really nice. Additionally, there's primitive caching implemented for conv, mapmul, and inner product operators. So if your models are heavily utilizing those functions, then you can also see an improvement in performance as well, since that reduces any redundant gem kernel initializations or additional torch overhead. And one thing I just want to note, I might sound like a broken record on this, but PyTorch has a bunch of other optimizations as well. So you might see optimizations across the board, regardless of the processor. But the ARM ecosystem is continuing to mature. So you'll see some more specialized optimizations like this PyTorch support for ACL. And so the latest versions, case in point with PyTorch 2.0 being the latest release, will include some more optimizations for Graviton compared to previous versions. Here's another nice graph. Pictures are 1,000 words. So here's the PyTorch inference running across a couple of our compute optimized families. And this is a graph for cost improvement. Just note that it's up to 50% improvement. So as you can see, some of the improvements are not completely 50%. So you might experience just a little bit lower, but overall, that's the most that you could get up to. And one thing I would like to note as well is the performance measuring that you would compare against all of these instances in terms of what is the equivalent kind of generation to look at. The C7Gs are going to be equivalent to the C6As and the C6Is. So it's just one number off. They're all the latest releases of instances. For the compute optimized family, this follows for other Graviton instance families as well. And the C5s will be the comparable instance to the C6Gs. Here's another graph for improvement in latency. Again, the first, third, and fifth bar is what we're going to look at for comparable instances. And then the second and fourth bar will be the same generation instance. Okay, so that's kind of the outcome that you can expect from moving to PyTorch 2.0 on Graviton. But what does this mean on a more practical level if you are using PyTorch 2.0, if you're a developer, and you're hands-on with this technology every day? The newest and main API that was released for PyTorch 2.0 is torch.compile. This is a new piece of additional code you can add. So torch.compile wraps your model and returns the compiled version. It's in the name, so it's not too much mystery behind that. But in the example code, you can see the initialization of a model on the right side, and you can just pass the model as a parameter. And this is completely optional code. You can upgrade to PyTorch 2.0 and receive other benefits that were added into PyTorch 2.0. This isn't the only one. You can also get there's a new high performance implementation for PyTorch Transformer APIs as well. So because the torch.compile is completely optional, that makes PyTorch 2.0 100% backwards compatible. There are some things that you want to be mindful of when you do upgrade. You'll have to upgrade a couple versions, and there's a few functions you want to be mindful of updating as well. And I'll cover those in following slides, so you're not totally blindsided if you upgrade to PyTorch 2.0 without upgrading to a couple other dependencies. But first, I want to break down the underlying technology that makes up torch.compile. So on the left side, the compiler breakdown, torch.dynamo is the new technique for acquiring graphs reliably and quickly. It takes a piece of code. Dynamo passes the code that can be compiled to the compiler, and any code that can't be compiled will be compiled with eager mode, which is what we or PyTorch now calls partial graph capture. And Torch Dynamo also ensures whatever graph is acquired is still valid. If there's a mismatch, the graph will be recaptured, and that's where AOT Autograd helps come in as well. AOT Autograd captures the backward part of the graph, as well as forward, but backward traces enables training. PymTorch brings the 2,000-ish plus PyTorch operators down to 250 primitive operators. And the intention behind that of bringing the number of operators down was so that there was a lower barrier to entry for developers who want to write a PyTorch feature or backend. Lastly is Torch Inductor. It's a new PyTorch compiler backend. Torch Inductor was designed to be Python native general purpose compiler that could scale and support a variety of hardware and operators. Now there's further Graviton support, so case in point. And Inductor generates Triton code on GPUs and C++ on CPUs. And for the purpose of today's talk, we're going to be focusing on the CPU aspect of it. So the reason I wanted to break down torch.compile is because of a new tool for debugging called the Minifire. And the Minifire produces snippets of code that would reproduce the original issue. So you could copy that snippet of code, add it into the GitHub issue for PyTorch repository, and you can get some help with a nice actual reproducible piece of code. And it's good to know a little bit more about what's underneath torch.compile, since you can also specify where you want to troubleshoot and get more specific troubleshooting. So you would just set an environment variable to see if the issue is being caused in AOT AutoGrad, eager, and just get a lot more specific recommendations. So as I mentioned, PyTorch 2.0 is 100% backwards compatible, but there are some things that you want to be mindful of. The recommended Linux kernel is versions 5.10 and above. This is more so for performance, getting the best performance on Graviton 3. Like I mentioned earlier, later versions are going to work better on Graviton 3. The ARM ecosystem is maturing, but it has not been around as long as x86. So the latest versions will typically have more ARM optimized features, and you'll be able to get a more bang for your buck on Graviton 3 since you will have higher performance. Python version 3.7 and CUDA version 10 will be dropped from PyTorch 2.0. So you'll want to upgrade your Python version to 3.8 and above. One more thing to note is that Python 3.7 was scheduled to come to end of life in June 2023. So make sure you upgrade Python 3.7 to 3.8, regardless of if you choose to upgrade to PyTorch 2.0. Here's a couple more changes to be mindful of on the code level. If you use ZeroGrad, the gradients will no longer be set to 0. It'll be set to none type. So if you are expecting zeros, you may run into an attribute error. And this is also hand in hand with optimizations made for Python or PyTorch 2.0, since this update reduces memory usage and increases performance, which I think makes a lot of sense since you're not storing a bunch of zeros and it's just being set as a single n type. Lastly, if you were using nn.parameter or torch.tensor to store attributes, torch.tensor and nn.parameter will now be serializing all the attributes. So if you do want to store attributes, use the tensor key dictionary. So if you want to know more about any changes to be mindful of, there's an extensive details on the PyTorch repository release notes and GitHub. So if you didn't get to completely take any screenshots, you can just head on over to the GitHub page as well. So let's talk about how to get started on Graviton. So there's a couple of ways you can get started on Graviton. You can use SageMaker and select the underlying instance to be Graviton, or obviously you can use EC2. There's also a few ways you can get PyTorch 2.0. You can use the AWS Deep Learning container. And the deep learning container comes with a bunch of optimizations, so it kind of lowers the amount that you have to be mindful of in terms of turning on certain Graviton 3 optimizations. On the right side is the Python wheel way of installing PyTorch 2.0. Couple things to note. As mentioned, the DLC already comes with optimizations, but on the last two lines of the Python wheel, export DNNL default FP math mode, that enables bfloat 16. So as mentioned earlier, bfloat 16 is a feature that's supported on Graviton 3. You'll have to enable it to take advantage of it. Last line, the LRU cache capacity. So if you're utilizing primitive caching to avoid the redundant primitive allocation latency overhead, just note that this caching feature increases memory footprint. So you'll want to just tune the capacity to something of a lower value if you want to reduce the additional memory requirement. All right, so if you do choose to use SageMaker, there are further performance and cost optimizations you can take advantage of by using Amazon SageMaker Inference Recommender. So this will provide instance recommendations based on your workload. It also conducts custom load tests across instance types and reviews the results. And lastly, it provides optimized endpoint configurations as well. Okay, so now that we talked about how we can start on Graviton, let's do a demo of that on how to install PyTorch 2.0 on some Graviton instances. And I will jump into that screen. Okay, so let's install PyTorch using the deep learning container on EC2 instances. I'm going to use this first instance. We're going to SSH in here. I'm going to move into my terminal. So I already have my EC2 key so I can log in. All right, now I'm in my Ubuntu instance. Prior to this, to set up my instance, I already added an instance profile so that there's permissions to read to ECR, since we'll be pulling down some images from ECR, and also ran a sudo apt update and installed the AWS CLI and Docker as well. So starting from here, one thing I want to note, just so that we're not rushing to follow along, moving to the AWS Graviton Getting Started GitHub page, specifically for the PyTorch section, going to scroll down. There's instructions on how to pull the AWS Graviton PyTorch DLC. So again, I already ran these updates, so we don't have to pay too much mind to that. But I'm going to grab this login command from ECR. And let's paste that in. Cool. So now that we're logged in, we should be able to pull this image down. I'm just using the command that was in the Graviton Getting Started guide on GitHub. This is going to take a minute. Cool. Now we have our image. I'm going to run a Docker image ls so I can grab the ID of the image. It's kind of cut off there, but here's the image ID, and I'm going to run the image in the background. Oops, not that. Run -d. Just going to run it in the background so it's not taking up our terminal space. So from here, we're going to grab the container ID. Just want to know what the ID is so that we can exec into it and run some commands through a shell. So now we have the DLC installed. Let's run some PyTorch benchmarks. I'm going to install the PyTorch benchmark from the GitHub repository. And this is TorchBench. There's a ton of models already in here if you did want to do some benchmarking. Sorry, I don't like when people scroll in recordings because it makes me dizzy. Thanks for bearing with me. I'm going to grab that GitHub link and do a git clone into my CLI. So earlier today, we took a look at some ResNet 50 models. So let's run a benchmark for ResNet 50. I'm going to cd into the benchmark directory. And from here, we can install and prepare the ResNet 50 benchmark with the python 3 install.py command. And that also might take a minute. After we install and get the ResNet 50 benchmark set up, going to install any dependent wheels. And one thing that I want to know about Python wheels, again, you want to make sure that you're using the latest versions, as most of the time they will have Graviton optimized considerations. And I'm going to let that run for a little bit. I think this doesn't take too long. But this is a dependent wheel to run the ResNet 50 command model, sorry. And this command is going to run the benchmark in JIT just in time. And the output will show us a couple metrics just to show that it was able to run ResNet 50. And we have the CPU total wall time and the CPU peak memory. And we ran all of that in the AWS DLC. So as I mentioned earlier, I'm going to click into the Python AWS Graviton Getting Started page. There's a little bit more information on just making sure that you have your environment set to grab the latest versions. So one thing to be mindful of is installing the latest pip version so it can actually pull down the latest Python packages. And if I scroll down, sorry, come down with me on a little bit of a dizzy ride here. Additionally, if you're running machine learning workloads, there's also a section on scientific and numerical applications. Again, latest version, I said it before, I'm going to sound like a broken record. You can run previous versions, but you're not going to get the best performance. Some versions, they won't have a wheel for Arch64. But even if they do consider upgrading, as you'll get better performance. There's also a section on Conda down here. So just wanted to surface that there's a lot more information even outside of the PyTorch section, because I'm sure you're not just using PyTorch, but using a combination of lots of other Python libraries. All right, so one more thing I wanted to go through is taking a look at PyTorch and using the DLC to create an extended DLC, because sometimes you want to have a couple other things in your Docker image other than just the base image. So I'm going to exit out of here and get out of this. Oops. All right, so now we're out of that instance. Let's jump into a new instance so we can start fresh and log in to try out an extended DLC example. Again, I've already run apt-get install, so I'm going to create a directory that we can work out of and create a Docker file. Select our base image. I'm going to use exactly the same image that we used to pull down. And then in the ResNet 50 benchmark, we also had to do a pip install of Numba. So if there's any other wheels that you're using and you want to have the image already installed instead of logging in to the instance and creating a shell, which is not typically what we do in deployment, but just wanted to show for demonstration purposes. Now we can do a Docker build. Let's just call it my special PyTorch DLC. It's a long name. Oops, sorry. I forgot to add a tag. Oh, I did not log into ECR. Okay. First, log into ECR. That this command didn't have had some escape parameters or escape characters that didn't let me log in. So okay, now we're logged in. So that means you can actually use the image, and we can run Docker commands as usual with the base to have it more customizable to your workload. It's already installing Numba, the dependent wheel we needed for the ResNet 50 benchmark. And now we have our special image, and we can run it just the same as we did before. Run it in the background and do a Docker PSA. So we just grab the container ID, we can actually exec into it. And then we can do a Numba version. Okay, so now that we have all the dependent wheels installed, we can just git clone the benchmark. Obviously, we can put this into the Docker file image as well. So we don't have to do this. Again, completely customizable. But from here, after we set up our ResNet 50 benchmark, then we can exclude installing any dependent wheels. It'll already have it jumped in there through our Docker file, and then we can run the ResNet 50 benchmark as usual. This is just going to take a second. And just like we did earlier, going to run the benchmark command as usual. Again, we didn't need to install the wheels, just to show that you can totally customize the DLCs to your needs, and got about the same result for the CPU total wall time. And that's how you would use AWS DLCs on EC2. Again, you can also run DLCs on SageMaker if you'd like, and take advantage of the SageMaker inference recommender. But that is my time for the demo. And now let's jump back to the presentation and see what we can expect looking forward, see where we can get updates. All right, now let's look forward into where we can take a look at updates, find further optimizations for PyTorch. If you want to check for updates, you can check out the AWS Graviton technical guide. It will share a ton of tips and tricks on frameworks outside of PyTorch as well if you are using any other technologies. There's also an in-depth optimization page on Python as well, like I mentioned in the demo. And in the pytorch.org website, there's a live Q&A series, and they're continuing to add new content. They go a lot more in depth into torch.compile than I did today. They also provide profiling and debugging on PyTorch 2.0 and also shows how to contribute to PyTorch if you would like to contribute to PyTorch as well. So that's the end of my talk. Thanks so much for listening and have a great rest of your day.